Well, welcome everyone. Our second lecture of the afternoon is going to be given by Shane Byrne. Shane is an associate professor at LPL and in this department that's bringing you this Summer Science Saturday. Shane is, I should say, Shane Byrne is not the same, not to be confused with the motorcycle champion. Anybody know him?
Unfortunately not.
You don't know him either. Okay. You're from the same part of the world, though, I think.
Yes.
Okay, so Shane is also the director of the Space Imagery Center. His research is in planetary surfaces. He studies surface processes, especially those that have to do with ices, various ices. And he is involved with the Dawn mission, yes, to this Dwarf planet Ceres. And maybe, Shane, you're going to tell us about Pluto as well?
I wasn't going to, but I'm happy to say a few words at the
end. Some of the geology of Pluto, maybe. Okay, very well. Take it away.
Thank you. Okay, let me know if you guys can hear that. Also, there are assisted listening devices for anyone who'd require them. If anyone wants one, just put your hand up, and Josh here will furnish those for you. So, like Renu said, I work on planetary surfaces, and most of that work is on Mars, but since this is a minor body sort of day, and Mars is not so minor, I'm going to talk to you about another project that I'm involved in, which is the Dawn mission to the dwarf planet Ceres. And not only did Dawn visit this dwarf planet Ceres, which is in the main asteroid belt, it also visited a very large asteroid called Vesta. The Vesta encounter is all done, so there's lots of results to talk about there. The Ceres encounter just started a few months ago, and we actually still have yet to get the best data from that, and I'll explain a little bit about the mission timeline as we go along as well. So a little bit about the science results, and a little bit about ongoing exploration, and a little bit about the spacecraft as well. Okay, so the point of the Dawn mission is to explore the asteroid belt by looking at these two largest members of it. Vesta and Ceres are the two largest asteroids, and Ceres has this additional designation as a dwarf planet, just like Pluto does. And it took about 214 years for the Ceres dwarf planet to get its first planetary mission there, and only 85 years for Pluto to get its first planetary mission there. So this has been a long time coming, but there's lots of interesting stuff to see there. So the asteroid belt, as Renu alluded to a little bit in the last talk, has a lot to tell us about the beginnings of the solar system. So Renu mentioned a lot about the orbits of the asteroids and what they can tell us about how the giant planets change position throughout solar system history. But the asteroids themselves also tell us a lot about what went into the planets, especially planets in the inner solar system like the Earth and Mars, etc. So these planets are essentially built out of asteroid-like blocks. They're put together early in solar system history within the first 1 or 200 million years, maybe at the outside for the Earth, and maybe even much shorter for smaller planets like Mars. And by looking at these asteroids, we get a chance to look at what the building blocks of our own planet actually look like. So the asteroid belt here, as Renu mentioned, this didn't come out super well, but are between the orbit of Mars, which is in the red circle here, and the orbit of Jupiter, which is in the orange circle here. All these little dots that you can barely see, unfortunately, are asteroids, and there's probably between 1 and 2 million asteroids in the asteroid belt that are bigger than a kilometer, and probably many, many more that are smaller than a kilometer, but you know, we really are interested in the more major objects here. Ceres and Vesta are marked in these ellipses here. They both got semi-eccentric orbits, so not quite perfect circles, especially Ceres, which is the outside one here. And they're both pretty much smack in the asteroid belt, but you'll notice that Vesta is on the inner edge of the asteroid belt here, a lot closer to Mars. So we expect that to be more rock and metal, things that went into the terrestrial planets like Earth and Mars here. And Ceres is on the outer edge of the asteroid belt at the point where water ice starts to become a major component of things in the solar system, like moons of outer solar system planets and Kuiper belt objects and so on. So Ceres has a substantial fraction of ice in it as well. So although these bodies are both in the asteroid belt and relatively close to each other, they're going to turn out to be quite different. Most of the asteroids that we've had spacecraft flybys look something like this. They're sort of irregular-looking potato-like objects with lots of craters all over them here. This is one of the larger ones that we encountered, Lutetia. But there's been a bunch of other smaller encounters, and most of these encounters have been just flybys of asteroids, usually when the spacecraft is on its way to something else deemed more interesting, quote-unquote. But a couple of asteroids that we've investigated in detail, like the near-Earth asteroid Eros, has been orbited and investigated. But like I say, most of these objects just really have the briefest of encounters with spacecraft that are flying by. The two objects that we'll talk about today, Vesta and Ceres, are enormous by comparison to these objects. So these literally are more like small or dwarf planets than the asteroids. So here's that Lutetia object that we saw on the previous slide, which dominated the previous slide. That's one of the largest asteroids in the asteroid belt. Yet, compared to these other objects, that's quite small, and all these other encounters that we've had, even down to points that are so small you can't even see them at this scale, like Itokawa there. These are typical of asteroids. These two large objects that we'll look at are much, much larger, and that's what makes them so much more interesting for us, because there'll be a lot more going on their surfaces, as we'll see, than just a cratered landscape from those other objects. Although they're very large by asteroid standards, these two objects down here now, Ceres and Vesta, are small by planetary standards. So these are only building blocks of planets. They're not as big as planets themselves. So you can imagine that you might have to put like 1 million Ceres-sized objects together to form something like the Earth, less so to form Mars or Mercury or the Moon. Well, the Moon actually formed in an impact from the Earth, but these planets were all built out of smaller objects like these asteroids. So there's a huge size gap between the biggest asteroid, Ceres, and what's the smallest planet in the inner solar system, Mercury. And many of these Ceres-sized objects went into this, building this. Okay, before we had these spacecraft encounters with Dawn, with these two objects, this is basically all the information we had about them. These are views from the Hubble Space Telescope. And you can't see an awful lot, right? But there's a few things you might pick out as curious looking, and then we'll see in up-close detail in a few slides' time what they actually turned out to be. So you can form your own theories in the meantime, and then see if you're right or wrong in a slide or two's time. So this is Vesta, and one of the curious things about Vesta is this extremely weird shape that it has near the South Pole there. So you can try and come up with some theories for that. And does anyone want to volunteer a theory before we go on? Come on, this is the fun part. People are always worried about being wrong, but actually being wrong is the best feeling in the world, because when you're wrong, it means something unexpected has happened, and you have the opportunity to discover something new. So, yeah, there's a guess at the back.
Possibly it doesn't rotate like Ceres does?
It rotates like Ceres does, yeah. So the North Pole and South Pole are at the top and the bottom of this image, so the equator is in the middle. So this strange-looking pointed feature is at the South Pole of Vesta. Product of a collision? It's a good guess. Lots of collisions everywhere in the solar system. Any other guesses? No more guesses? Oh, that's too bad. Oh, well. Okay, Ceres here, slightly larger, but further away, so we really don't have good views of that from the Earth. But you can see a few things going on the surface of Ceres. You can see there's different colors here versus here. So there's some kind of changes in composition on the surface. There's also bright spots that we can see in the Hubble observations that we don't really know what they are on the surface either, but we'll see that later on in the talk. And the answer turns out to be we still don't know what they are, but they're even more interesting when you see them up close. Okay, and these guys are the discoverers of Ceres on the left and Vesta on the right. The dates are sort of interesting here. These are early 19th century discoveries, and when they were actually discovered, people were certain that they had discovered another planet, and so certain that they had basically designated Ceres as a planet. This was even before the discovery of Neptune, one of the outer solar system planets. So Uranus had been discovered just 20 or 30 years before that. So people thought they were on a planet discovery spree here, and Ceres was just one of those planets. Like you saw in the earlier picture, there's a big gap between Mars and Jupiter. So people had expected, based on an empirical theory called the Titus-Bode law, that there would be a planet in that area. So when Ceres turned up, everybody was primed to believe that it was a planet. Later on, other objects like Vesta started to be discovered, and people were going, okay, so there's more than one planet. By the time the 19th century ended, there was close to 500 of these objects, and people were like, okay, I guess they're not planets after all. So they all got demoted to be called asteroids, and now make up the asteroid belt that we know. This is sort of analogous to the Pluto situation that we have today. Pluto discovered in 1930. Everybody jumps to the conclusion it's a planet. By the end of the 20th century, now there's a couple of hundred objects known out there, and people are like, okay, I guess Pluto's not a planet either. So history's sort of repeating itself there, a little bit offset in time by about a century or so. Okay, so Vesta, like I mentioned, is on the inner edge of the asteroid belt, so we expect this to be mostly rock and metal, the stuff that goes into making planets like Earth and Mars. The metal goes into making our core, and the rock goes into making the thing that blankets the core, the mantle that we call it. The neat thing about Vesta is, though, you can actually go outside into the atrium and see what Vesta is made of if you want. There are meteorites out there that were blasted off the surface of Vesta. They migrated their way through interplanetary space, and they ended up falling on the Earth, where we picked them up and put them in our meteorite collection. And we're pretty sure these are from Vesta, because if you take a spectrum, which is basically to look in detail at the colors of these objects, of the asteroid and the meteorites, they match up. There are also good evidence from the Dawn mission that these come from Vesta as well, that I'll talk about a little bit later. But if you actually want to see a chunk of this asteroid that we're talking about, then it's right outside. Ceres, on the other hand, is slightly further out in the asteroid belt, where things were colder when it formed, so it's expected to contain a lot of ice, and also expected to have liquid water early in its past. It's quite likely, actually, that Ceres had a global ocean early in its history, much like we think the moon of Jupiter, Europa, has today. And that global ocean may or may not be completely frozen at this point, but the Dawn mission, again, will tell us more about that. Ceres is expected to have a rocky core and an ice mantle, rather than have an iron core and a rock mantle. Okay, let's see. All right, so Dawn's mission then is to investigate these two objects, and we've got Ceres, which is possibly the building blocks of what the cores of the giant planets would look like, and we've got Vesta, which is possibly a building block of what the terrestrial planets would look like, both from different areas of the asteroid belt. This is a picture of the Dawn spacecraft here. It has these humongous solar panels because we're far from the sun, and we need all the square inches we can get to collect solar power and power the spacecraft. Dawn is the 9th mission that NASA has sent as part of this program called Discovery, and this is the low-cost version of planetary science, where these missions are small. They've got one really dedicated task, and they go and they do that one task very well. So they're not the giant flagship missions like the Curiosity rover that went to Mars, but they're very small, focused missions. And so it's sort of like flying, a low-cost airline or something to get to where you want to go. You don't get the peanuts and the meal, but you get to where you want to go. So just think of that when you think of these missions. Okay, so we launched then in 2007 on a Delta II rocket. And this is just a little picture of the launch. And Delta II rockets are great for inner solar system exploration because they're basically off-the-shelf rockets, and they go wherever you want them to. They've got on these strap-on side boosters here. They'll give you a little bit of extra power. So I think we had 9 strap-on side boosters because we had to go further away than is typical for an inner solar system mission. We were going all the way past Mars and into the asteroid belt. The route that we took was a little circuitous, but you can see it in this animation here, and I'll try and talk along with this. So here we have Earth and Mars and Ceres, and Dawn is launched here. It does a close approach by Mars to get this gravitational slingshot, picks up some speed from Mars, and gets thrown out toward the asteroid belt. So its first target here is Vesta, and we're going to rendezvous with Vesta in or around 2011, 2012. We go into orbit around Vesta for a while. This is Ceres right here, so now we're getting close to Ceres, and people are thinking about leaving. We've got to catch the bus, the interplanetary bus, to the next asteroid, and that requires careful timing. So here we go. We're leaving Vesta at this point, and we start to drift outwards, and we rendezvous with Ceres. And that rendezvous happened just in March of this year. We got into orbit around Ceres in March 2015. So we've really just arrived, and a lot of the stuff you'll see on Ceres in this talk is pretty preliminary still. Okay, so a couple of firsts for the Dawn mission. It's the first time we've orbited a main belt asteroid. So these are, like I said, building blocks of the planets, but also the source for our near-Earth asteroids that we'll hear more about in the next talk. And near-Earth asteroids are the source of things like mass extinctions on the Earth, so we definitely want to know about that. Also, Dawn is the first mission to reach a dwarf planet, although only by a couple of months, but we can still say that, right? Because New Horizons didn't get there until a couple of days ago. So we started orbiting around Ceres in March, like I said, so we got squeaked in there just in time. The instruments that we carried are a camera. Most of the data comes from the camera. We also carried a gamma ray spectrometer. This tells us about the composition of the surface in terms of what elements are making up the surface. And then we also carried a spectrometer which tells us about the minerals of the surface, so chemically what things are made of as well. Most of what we'll talk about today, though, is the camera data. As well as just taking pictures, we take pairs of pictures from different angles, so we get a stereo pair of images, and just like your eyes take pictures of things from slightly different angles, that allows you to see in 3 dimensions, and that allows us to see the surface of these objects in 3 dimensions as well, so we can figure out the topography of these asteroids too. Okay, so this was the biggest interplanetary spacecraft that we ever launched, but really that's because of these enormous solar panels. Like I mentioned, we need all these square inches to get power for the spacecraft. As you go further out in the solar system, people give up on solar panels entirely and they use nuclear power sources. But you can just about do the main asteroid belt using solar panels. So we're sort of pushing solar panel technology to its maximum here. And that's why we've got these enormous things sticking out of the spacecraft, which is much smaller. It's over here, just on the edge of the field of view. One of the neat things about Dawn is that it has this very futuristic propulsion system. So this is kind of Star Wars-y, you know. It's usually we use chemical rockets, and well, I should back up. You know, I say it's Star Wars-y, but I said that to somebody outside planetary science, and they told me everything you do is Star Wars-y. So, so you know, it's all very subjective, but I think this is very Star Wars-y, right? So, Dawn works by this ion propulsion system, which is using very small amounts of fuel, xenon ions in this case, that are accelerated to very high speed as they leave the spacecraft. So Dawn can go from 0 to 60 in several days. It's not exactly not exactly a sports car here. Yeah, 0 to 60 in 4 days. So slow and steady wins the race, though. So just like the tortoise and the hare, the tortoise is still walking long after the hare has fallen asleep. And we can get to places using this propulsion system that we really can't take enough chemical rocket fuel to go to. So this is really what makes this sort of mission possible, because not only were we able to get into orbit around one object, but we were able to leave orbit around that object and get into orbit around another object. I'm not entirely sure about this, but I think that's the first time we've sent a planetary mission that orbit 2 separate objects in the same mission. Okay. All right, so we orbited Vesta in 2011, 2012. So I'll talk about Vesta for a little bit. And like I say, there are chunks of Vesta right outside if you want to go see them. This is the size of Vesta compared to something a little bit more familiar. So there's New Mexico, and there's Vesta. Vesta is named after the Roman goddess of hearth and home. A lot of these asteroids are named after Roman figures, actually. And this is what we expected to see when we get to Vesta. So like I said, we expected this iron core, we expected this rocky mantle, and then on the surface, we expected something very different. And what we expected came about from looking at these meteorites that I mentioned out in the atrium. And what they show is that Vesta had volcanoes active on its surface. So the entire surface of Vesta is actually covered in stuff that's like a lava flow. So if you've been up to Sunset Crater in Flagstaff and you've seen the Bonita lava flow there, the surface of Vesta looked something like that early in its history. And that's very unusual. Most of these asteroids didn't have volcanoes on their surface, and yet these volcanoes on Vesta were active just a few million years after the solar system really got started. Okay. It's also true that more meteorites from Vesta have reached the Earth than from the Moon and Mars combined. So that's cheating a little bit because Mars is really hard to get material off because it's a big planet. But we've got lots of rocks from the Moon because that gets hit a lot and it's right next door. So it's kind of interesting that we've got all these samples from Vesta. We know much more about Vesta than we know about some of these other objects. So the type of meteorites that we have outside are called, there's three types actually. There's Howardites, Eucrites, and Diogenites. As a group, they're called ATD meteorites. And here are just two of the ones that we have outside, so you can find these later on at your leisure. This is a Howardite up at the top and a Eucrite down at the bottom. And what we think is going on the surface of Vesta here is that we have Diogenite material deep down. The surface, these lava flows that I talked about, are made up of the meteorites that are called Eucrites. And then when you blast craters into the surface of Vesta and you have ejected from that crater, so basically a shocked version of the crust, then you produce these Howardites. So we already had a pretty good idea of Vesta's history before the New Horizon, before the Dawn spacecraft actually got there. And these impacts that blasted holes in the surface of Vesta here are basically everywhere. You can see impact scars all over the surface of this object. So it's thoroughly pummeled in craters. This is a photo mosaic from the Dawn data. And here's this strange object that we saw near the South Pole again. So we'll get an even closer look at that in a couple of slides' time. But these impacts have completely reworked the surface. So any volcanoes that used to be there have been basically bashed into pieces and are no longer really visible. But the chemical signature that they were there, the composition of the rocks, tells us that there used to be volcanoes all over Vesta, basically that this is all volcanic rock. Okay, you'll also notice that there are these troughs here. It's another interesting feature of Vesta that I'll try and explain in a couple of slides' time. So we've got craters, we've got troughs, we've got this big enigmatic thing at the South Pole, and lots of things that are available for Dawn to examine up close. So the craters are pretty much standard impact features that we see on every planetary surface. Here's a couple of examples from the surface of Vesta. So here's a small crater that's a fresh one, so you can still see this dark blast pattern around it. You can also see a lot of craters that look like this on Vesta, where the upslope side is all sharp and then the downslope side has been covered by ejecta from another crater. So there are craters overlapping craters. It's like this big layer cake of cratered crust. And these craters get slowly erased and buried over time and replaced by other craters. There are also these large cliffs near that south polar feature here where we see material slumping off the walls. So even though Vesta is a very low gravity environment, there's still landslides going on. You might be able to see this more clearly in these views at the bottom. This is topography here that we got from those stereo images, and where red and white are at the high elevations and blue are at the low elevations there. So you can see this material is slumped downhill in that perspective view. Okay, there's also a couple of whimsical things that you can see. You know, people are great at doing this. They just see shapes and patterns everywhere, and this particular one reminded someone of a snowman. So we've got snowmen on Vesta, despite the fact there's almost zero ice on Vesta, but not to worry. Okay, so let's take a look at that big feature in the south. And John, your guess is correct. It's a giant impact basin. Two giant impact basins, actually. So this is the Rhea Silvia impact basin, and this thing in the middle is a central peak. So this happens with very, very large craters where the crust basically rebounds in the center after you dig this enormous hole out of the object. Now, this is a huge impact basin compared to the size of Vesta. So if this happened on the Earth, like if we were to scale Vesta all the way up to the size of the Earth, then this crater would stretch from Washington, D.C. to Japan. So Vesta basically barely survived this impact, and it's possible that this impact is a source of a lot of the HED meteorites that we have here on the Earth, because so much of Vesta was basically blown off into space in this one event. And there's a whole family of smaller asteroids surrounding Vesta that are actually just chunks of what Vesta used to be. So Vesta is, it's not exactly a shadow of its former self, but it's a much reduced version of its former self due to this one impact. There's also this other impact, you can sort of see the outline of it here, that predates the Rhea Silvia impact, but also was a major event in Vesta's history. That mountain at the center is also one of the biggest mountains in the solar system. I mean, we can see it with a telescope from the Earth. It was that big. So this is a perspective view of the topography again, looking across Rhea Silvia. So you've got the low area of the crater and then this giant mountain in the center. So this would be the mountain on Vesta. This is Hawaii for comparison, and including the part of Hawaii that's underwater, because most of Hawaii is still underwater. But also, it comes close to the largest mountain in the solar system, which is Olympus Mons, this large red outline in the background. So that gives you an idea of how big this thing is. This is a little over 15 kilometers high from base to top, so close to 10 miles in height. So it's a significant feature. Okay, so we also see rugged topography everywhere with smaller impacts, and these grooves that I mentioned, which don't show up super well here, but you can see them sort of angling down to the right here in these sort of areas of the planet. And the grooves themselves are also related to what's going on with these very large impacts. So when we dig that giant hole out of Vesta, then things start to collapse toward the center of the holes, and that makes these tectonic faults that are circumferential to the centers of these impact basins. And if you map out these grooves here, like say in the white, and this other set of grooves in the red, and you think of these as giant circles going around Vesta, and you plot where the centers are, then the centers all cluster together for one family of grooves. They all cluster someplace else for the red family of grooves, and the location where they cluster is right in the center of this impact basin. So all these grooves are basically just circumferential to Rhea Silvia. All the ones that are mapped in red here are circumferential to this much older impact basin that's down here that Rhea Silvia overprinted to some extent. So most of the geology of Vesta, the physical geology, can be explained in impacts, some of them giant impacts, and the chemical geology in terms of this ancient volcanism that's going on. The chemical geology is advanced as well by John, because we can get compositional maps of the surface. So this comes from that near-infrared spectrometer that I mentioned. And if you plot where those compositions on Ceres lie, so this is all the colored points in the background here, and the axes here are not super important. They're just different chemical markers we use to identify objects. And these ellipses are where the different types of meteorites would fall. So these are Diogenites. In the middle, it's Howardites. Up here, it's Eucrites. So most of these points are Howardites. And so the surface of Vesta is pretty much made up of this Howardite material. So if you go outside and you look for Howardite meteorites, then you're basically looking at a piece of the surface of Vesta. So Howardites were the things that have been excavated out of impact craters, and they've gotten a little bit shocked by that. And they got blasted into space and eventually found their way to Earth. Okay, so now onto Ceres. Like I said, we got to Ceres in March, and we're going to be there until about a year from now. After that, it's not quite clear what's going to happen. The spacecraft may run out of fuel. Dawn is, like any spacecraft, it sort of, picks up things as it advances into old age. It doesn't quite work as well as it used to. And one of the things that's not working quite as well as it used to is what we call a reaction wheel, which controls the orientation of the spacecraft. So a lot of the orientation control now we're doing by firing thrusters, and that uses up fuel faster than we would like. But we're definitely going to make it to the end of the mission in July 2016, but after that, we're not entirely sure. This is Ceres rotating in the background. There's lots of interesting features here that are rotating past. Also lots of grooves, also lots of craters. And we'll take a look at a few close-up things as we go along. Ceres is a dwarf planet, the only one in the inner solar system, or that's been designated a dwarf planet so far. So Ceres and Pluto form this pair for the inner and outer solar systems, for the asteroid and the Kuiper belt, respectively. It's the most massive asteroid, the first one to be discovered, and physically the largest one as well. And this is what we expected the interior of Ceres to look like based on its density. So we expected a rocky core, we expected this thick ice blanket around it, and then we expect the surface to be a mixture of dust and ice. And a lot of meteorites that have fallen onto Ceres are mixed up in this outer crustal layer here. This is going to be very interesting. When we get more data around Ceres, we'll be able to say more about this ice layer here in the middle. At one point, this was all liquid water, and it was just a global ocean surrounded by this ice shell. There may be a small amount of liquid water still left on Ceres, and so there's the possibility for life with liquid water in contact with warm rock in the center. So believe it or not, there may be an ocean and life on an asteroid, which is kind of something to wrap your mind around. At present, though, the surface is quite cold, and we suspect that this may be completely frozen through now. But we'll know for sure later. Ceres is named after another Roman goddess, this time goddess of agriculture. And so a lot of the place names that we're labeling now on Ceres, because we've got to attach labels to everything that we find. That's another human tendency. So everything that we name on the surface of Ceres now is going to be named after harvest deities from around the world, or agriculture deities from around the world. Okay, so this gives you an idea of what the entire surface of Ceres looks like. This is unwrapped into a standard sort of map projection where the North Pole is along the top here, South Pole is along the bottom. It's winter at the South Pole right now, so you don't see all the way down to the South Pole, unfortunately, but we'll be there long enough so the seasons will change on Ceres and we'll get a better look at this part of the planet. You can see craters everywhere. These blue areas are low, so these circular blue areas are craters. And you can see a couple of grooves similar to what Vesta's grooves look like, but like say coming out of this crater here. But they tend to be shorter and not as significant as the Vesta examples. Okay, the real interesting thing about Ceres, though, is not so much the topography, but looking at what the body looks like. So when we saw those Hubble pictures, I mentioned there was a couple of enigmatic bright spots that we couldn't explain. So this is what they look like in a little bit closer up. So there are some areas that are extremely bright, much brighter than the rest of the surface. You can sort of ignore this down here. This is not real. This bright area is just a processing artifact. Most of Ceres is quite dark. It has reflects about 9% of the light that hits it, so it sort of looks like asphalt if you were to look at it. But there are some areas that look bright, not as bright as freshly fallen snow, but maybe as bright as this wall over here. They're quite bright. One of these areas here, this one here, is extremely bright, and it's in this very dark surrounding area as well. And when we zoom up on that, what we see is kind of interesting. We see this just bright material at the bottom of this crater. This is an animation put together by somebody in the public who just took our data and made this really neat perspective view. So the bright spot is being held in the center of the image here. Usually the spacecraft is flying around here, and the surface is moving, but here the surface is being kept fixed, and your point of view is moving. So, like I said, these bright areas are several times brighter than the rest of Ceres. And does anyone want to hazard some guesses about what they may be? Ice. Ice is a good guess. Yeah, I don't have the answer, so any guess is a good guess. Other guesses? Other guesses? Yeah. Well. So everybody wants it to be ice. I want it to be ice because I love ice and do all my research on ice. So ice is probably still the number one contender, but it's hard to understand how it would still be there because the temperatures at this location are quite warm, so warm that probably every year several centimeters of ice would ablate away. So unless it's a very recent exposure of ice, like this ice got there very recently, then it's unlikely that ice could really survive for very long periods. So it's a mystery, but we don't really have any better ideas either. Another possible idea is that this could be salt. So I mentioned that there might be this global ocean on Ceres. So you can imagine if you had somehow a break in the crust and salt water can come up here, So all the water can evaporate away, or if it freezes to ice, the ice can ablate away, and salts can be left concentrated on the surface. And salts also appear bright and would appear bright in these images. So it's still a mystery, but those are the two leading hypotheses. So this is a zoom up of that spot here. At one point, we thought that it was bright even after the sun had set on that location, like it was actually glowing, but it turns out that it's just on a slightly high-standing piece of topography. Well, that would have been really interesting if it had been glowing by itself instead of just reflecting light. But this is probably the number one mystery that we're working on now. And like I said, we've only gotten the first slew of data from this encounter. As time goes by, we'll be reducing the size of Dawn's orbit around Ceres. So now we're getting images where each pixel in the image is maybe 100 or 200 meters. By the time the end of the mission comes, we'll be getting pictures where the pixel sizes are close to 10 or 20 meters in size. So we're going to have a massive increase in the image quality here, and that's going to tell us something, hopefully what we need to know to figure out what's going on here. Either way, it's very interesting because either the water is coming from somewhere very recently, like maybe Ceres interior, or the salts are being actively deposited on the surface. In either solution is very interesting for us. There's a couple of oddball features on Ceres as well, like here's a pyramid-shaped structure that's just out in the middle of nowhere. So we're not entirely sure what this is, but this material is sliding off the edges of this steep slope, and it's bright underneath. So again, this could be ice, and it could be that the entire crust of Ceres is a lot more ice-rich than we were expecting. And if you basically scrape off a little bit of the dirt here, and this is dirt that's accumulated over billions of years from meteorite infall, that you could find ice. And these streaks here look like they're basically, this is basically locations where things have landslided off this pyramid-shaped object. We don't really know what's going on. If anyone has any more suggestions, I'm really happy to hear them. In fact, I'll probably write them down if anyone has any good ones. But this is the sort of thing that we'll be investigating over the coming months or year left at Ceres. And just to give you a flavor of what's happening, this is the mission timeline. So we're around here now in mid-July 2015. And we've done these stages in the mission, which is basically these very high altitudes, like 13,000 kilometers high, 4,000 kilometers high, and those have given us those low resolution pictures. Right now we're doing this transfer stage into a high altitude mapping orbit, so that will be 1,400 kilometers high, and eventually a low altitude mapping orbit of about 375 kilometers high. So we'll be all the way up. We'll be all the way down from 13,000 kilometers to 300 kilometers above the surface. So getting closer and closer, we'll get better and better images. This will be all in early 2016, so we'll get the best data then. And like I say, the mission wraps up somewhere around here in early summer 2016. We also go into a solar conjunction at that period, which is when Ceres, as viewed from the Earth, goes behind the sun. And that means communications will be shut off at that point for maybe a month or so. With the spacecraft in its final orbit and the communication shut down and its goofy reaction wheel and our fuel running out, that may be the end of the mission, but it's also possible that NASA will extend this so that we can do some more observations in this in the fall of 2016. Okay, so one thing I just want to put up before we break for questions is where you might go to find more information if you're interested about Dawn or Vesta or Ceres. There's the mission website, which is dawn.jpl.nasa.gov. Yeah, apologies, that's a J. It's sort of hard to make out there. And that will give you lots of extra information about all of these things, probably more than you can ever read. So I'm happy to take any questions, and thanks for your attention. All right. Mary, there's a guy at the very back. Yep. Would you go ahead in the green T-shirt, and then we'll get that.
I was curious why the IR imager hasn't produced any information about the white spots on Ceres.
So far, they're not able to get measurements of those white spots because we're too far away. So this framing camera has pixel sizes that are very small, so we get high-resolution pictures And the infrared images has pixel sizes that are huge. So the white spot is just a tiny part of 1 pixel, and it's mixed in with the rest of Ceres, so they just can't tell anything about it yet. When we get down to the low altitude mapping orbit, though, they'll see it clearly, and then we'll have an unambiguous answer.
On a similar note about the low altitude, is that a stable orbit at 375 kilometers? It seems pretty low.
It's pretty low, but it's probably stable, and I say probably because we don't actually know the gravity field of Ceres in a great amount of detail yet. But based on how likely irregular the gravity field is, it'll probably be stable for quite some time. Yeah. All right, right at the back.
There seems to be the possibility of so much water on Ceres. I was wondering if, maybe they should be spending more attention on Ceres than Mars as far as, possibility of people actually being able to go to some place, get water to use, things like that,
Right. Yeah, so it's an interesting thing about where to send people in the future, right? So Mars is much closer, so it's much easier to get to, and it also has abundant water. But one of the major rationales for sending people into the solar system may be to one day mine asteroids for platinum group metals, maybe the only economically valuable thing we can get from them. And if that's the case and you want bases in the main asteroid belt, then Ceres would be a great place to go. Abundant water ice and enough gravity so that all of your structures and things don't float away, which would be like really annoying. Yeah. Okay. Yeah, questions?
You mentioned ice. What's the temperature on the surface?
Temperature on the surface of Ceres varies quite a lot, both because of day and night variations and also because Ceres is closer to the sun at some points in its orbit than others. But let's see, I don't recall what this would be in Fahrenheit, but the temperatures here in this room are about 300 Kelvin, and down on temperatures on the surface of Ceres would be about 150 Kelvin. So the temperature is about half of what it would be in this room, so quite cold. Definitely below the freezing point of water, or even things like carbon dioxide would freeze out at those temperatures.
So what happens to the spacecraft after you end the mission? Is it likely to crash on Ceres?
Yeah, it could possibly crash on Ceres, but then if we do come across or come to the conclusion, let's say, that there's a liquid ocean underneath Ceres, then we would want to avoid that situation at all costs, right? Because we don't want to contaminate it for some sort of future astrobiology investigation. So in that sort of situation, we'll probably do what they've done for Martian spacecraft in the past, which is to boost their orbit up to some very high altitude using the last remaining fuel and park it in a very high altitude orbit so that it's very unlikely to ever hit the surface of Ceres. At the moment, though, the plan is just to leave it in the 375 kilometer orbit, and we'll know better when we get down to those altitudes how long that's liable to last. Any questions? Oh, question up here, yeah.
It looked like Ceres was in the asteroid belt most of the time, or at least a good amount of the time.
Yeah.
So how dangerous is that for the Dawn to not get hit by one of those?
Right, yeah. So, this was a big source of concern when we were sending our first spacecraft through the asteroid belt, which I think were the Pioneer series of spacecraft. And people at the time didn't know if a spacecraft would make it safely through the asteroid belt, because we could see the big ones, and we knew there were lots and lots of small things in the asteroid belt too, but we didn't know how much. And so far, every spacecraft that's been sent through the asteroid belt has gotten through without incident. And Dawn's no exception. It went from one asteroid to the other, and it didn't hit any of the small stuff that we know is there. So it's likely the asteroid belt is pretty safe for spacecraft to travel through. I always think of that scene in Star Wars, Darth Vader saying, "Asteroids do not concern me, Admiral. I want that ship." All right, yeah, one more question.
The ring is on Vesta.
Mm-hmm.
Does that indicate that the surface of the planet would be sliding down to fill in that impact?
Right, yeah, that's exactly what people think has happened. You dig out this big hole in the ground, and then you have these slumps, basically, as the rest of Vesta tries to slide downhill and fill those in. And the, like I said, the orientations of the scarp basically tell us that it was sliding in towards the center of those features. All right, so is it 3 o'clock, Mary? I can't see the time. Oh. Thank you. So in a few minutes, we'll start the next talk. I'll give people a couple of minutes to get up and stretch their legs and so on. In the meantime, I'll just play this video so that you can get a tour of some of the features on Vesta that we've talked about. And thanks a lot again for coming today.